we'd done just the mass, just to review, and then we had, I used to just have it like that, but I constantly draw this set of springs, motor of some sort. Amplifier. I've got to learn to draw the right size boxes. But the reason it's going to fit is because I'm also going to call it a drive. You'll notice that there's two different terms that get applied. One is amplifier, one is drive. Drive is, put a little asterisk, drive tends to be for steppers and it's open loop because you are driving current into a load, which actually you don't. I mean, you can't drive current into a load. You can apply a voltage and current is drawn in by the amount of the resistance, but you can't just push current down to a load. There's got V equals IR kind of wins. But the, I'll put a 2 here. The amplifier tends to refer to closed loop systems because you're truly looking at errors that happen over in the motor part of things and between where it is and where it's supposed to be and adjusting or amplifying a signal. In the stepper system, you're not amplifying anything. What you are doing is you've got wires that need to go from here to here, but did you look to see on your motors how many wires there were going to that motor? You got 6?
2 sets of 4, I think.
Yeah, 2 sets of 4, the 8 wires. Some of you have 6 wires. I don't think I have too many that have 4. 4 is a very common number, but I don't often use in lab the 4-leaded motor because it's not near as flexible as the 6 or 8-leaded motors. So you have 6 or 8 lead motors, and you're going to have to figure out how that actually works. And I'm going to show you kind of how the windings work in a motor. But essentially, there's pairs, and one's going to each end of the winding. So you may have gotten into in the motor itself. Let's just talk about a stepper motor. In the motor itself, electrically, you're going to have a phase, what's called a phase A, and you're probably going to have, those are coils, couldn't tell, a phase B. So it's not, remember how many wires come out of a DC motor?
2.
2 wires, right? Apply voltage, it spins. And that whole part of aligning the magnetic field of the magnet with the electromagnetic field of the coils. And I do use those words distinctly separate. Electromagnetic to me, now that's the coils versus magnetic field of the permanent magnet. As those align and move around, it magically spins. It's not magic, it's called commutation. But in the stepper motor, we have 2 phases, an A and a B. So we don't have a single phase anymore. We have 2s. So it is called a 2-phase motor, okay? 2-phase. And what that means is to make it work, you need to manipulate both the A phase and the B phase. Well, this looks a lot like, this right here looks a lot like the middle part of that H bridge. And it is. And so there's kind of, shouldn't surprise you that the H bridge that you might run a stepper with, that L298N, which I gave some of you, so I'm not really giving it away at this point, that is a 2-phase H bridge. You could buy a cheaper one that's single phase that would run a DC motor. You could run a DC motor off that H bridge by hooking that single phase to it and ignoring the other phase. But in this case, we need both phases hooked up. Now, the tricky part to a stepper motor is that there's a 4-step sequence. I'm going to first describe what happens with to run let me take a step back. Let me finish up the picture so you know what's going on, and then I'll come back to the motor, okay? So on the picture, the other part over here is some sort of controller. Now, typically you probably have, this is where you're plugging into an operator interface, or you may be plugging into your PC to program it. This controller also may have inputs, and it also may have, and I'm going to say, in this case, generally, I'll call them general purpose inputs, and they can be digital or analog. And if it has inputs, generally it also has outputs. And those can be digital or analog. In digital, the inputs part of things are typically your switches, your sensors, you know, things that's responding to push buttons, e-stops, limit switches. That's the inputs, digital. The outputs are, you know, telling actuators to go. Again, it's electrical outputs that in order to actually control something eventually that's mechanical, you're going to have some conversion. And in the case if you want to make a motor move, that conversion is electromechanical conversion. And then, of course, inside of this whole thing is microprocessor that you're programming in whatever program fits. And there's lots of motion controllers that are specific for motion control that do a really nice job at the acceleration of a motor, keeping track of position. There's a bunch of things that you'll learn as we go throughout this semester that are just common to motion control. And it's really nice not to have to recreate the wheel, just buy a motion controller that all the stuff's just ready for you to use, as opposed to applying a microcontroller to do this function. That means go find libraries and hope that whoever wrote those libraries did a good enough job and that they point directly at what you want to do. Now, at this point, my experience is there's some pretty good libraries, and there's some libraries that don't do a very good job with especially the acceleration part of things, of motors. They're designed for turning on an input, but they don't really know that there's mass attached to that, or turning on an output. But as soon as there's mass attached to an output, if you want to make the mass move, which is what this class is all about, you have to deal with acceleration. And that's the tricky part. And so you can't just go on. You've got to accelerate it at a rate with a certain amount of torque that you have available. So as you look to your microcontroller, you're going to want to look for something that has a segment of it that can handle a motion profile. You're telling it how far to go, how fast. This is basically all those parameters that are in your kinematic equations. All right, I'll do, you know, acceleration, velocity, distance, direction, and time. There you go. Time. Exactly. Got it. Thank you. Yeah. So, and with, you know, you guys have applied those a fairly good amount, I presume. They're handy enough that when I wrote my motor sizing handbook, which is on the Mechatronics Center website now, you can just go use it. I used to keep it really secret because I made money knowing how to motor size, and I wanted people to pay me to motor size. In this system, there's going to be some communications. All right, you got to pick some network, some communications. I'm going to specifically call this a protocol, a communications protocol. There's we're using communications protocol. We're using multiple communications protocols right now. I'm talking. That's English. I make sounds. You understand the sounds. That's a communication protocol. Obviously, there's digital bits and bytes. There's the internet that we're using. There is there's networking that you can have packets go across. If you have lots of information, if you have simple information, this might be as simple as a digital signal of a frequency where each pulse means something, and it could be an analog signal where you have actually data in the analog signal that gives you a value, right? Because if you ever want a value to transfer from this to this, it's not a digital bit. It's got to be either a digital word, and then you put it on a network communications protocol, or you can say a value through an analog method where the value of the analog signal, whether it's a current signal or voltage signal, can also be interpreted on the other end, and they get the value correct. So there's lots of different communications protocols between these two. The key is they have to match. And so if you're using components where this controller was made by one manufacturer and the amplifier was made by another manufacturer, suddenly the burden is on you, the engineer, to make sure that those two are using the same protocol. You guys have had lots of experience with network protocols and trying to get communications. You've done RS-232, you've done I2C, hopefully you've done Ethernet. I don't know, have you done Ethernet? Have you done USB? Have you actually had to dig down into those protocols to figure out what they're doing? I'm using this little pen, this little Bluetooth. There's another protocol right here. There's a little radio in this thing. And, pretty cool technology, but here it is. It's a network communications protocol that's telling the computer all the different, how hard I'm pressing and where I'm, it's another protocol. So the standard one in stepper motors that you use, this protocol, the standard one is called step and direction. Okay, and it's actually two wires. It's two. So this one would be, this one would be direction, and this one would be step. And so the reason this is called step and direction in a stepper system is because the motor itself is a natural positioning. It's not a spinning device, it's a positioning device. A DC motor, when you just apply voltage to it, it spins. Even a DC brushless motor, after you've commutated, you apply voltage and it spins. An AC motor, you apply the alternating current voltage and it spins. All of a sudden, when you want to try and control position of something, you need velocity over time. And that's not usually, velocity over time gives you distance, right? But it's not usually precise enough distance to do any actual positioning with. So we're always looking for ways to actually control the motor shaft within millidegrees, very tiny steps. We have the ability now to easily turn this motor shaft on the stepper motor when we do microstepping. If we did set our microstepping, for instance, at 25,000 steps per revolution, it's a very easy, you do some manipulation of the coils and you can do microstepping, and that motor now will stop and have stiffness you could tell it to go 14,000 steps and the shaft moves over to here and it locks right here. It's a natural positioning device. But the downside of that is that you have to, if you're going to tell it where to go, you have to have some sort of signal to tell it how many steps should you go. it's not a spin, just turn on and spin. If you want to make it go 1 revolution, spin 1 revolution, you don't tell it to spin for velocity over time. You tell it to go an exact number of steps, which is why they call it a stepper motor. So this step and direction is a digital signal. It's digital. The steps, the number of pulses corresponds to the distance. And the direction's kind of obvious. If it's high, it's an on-off signal. If it's high, it goes one direction. If it's low, it goes the other direction. And the direction is based on kind of how you set it up. So direction is just, that's the easy one. The magic one is the step. But so what that means is if you're going to move this motor some fixed distance, this drive will need to sequence these phase A and phase B coils in such a way that it moves it in an organized fashion. And the microcontroller needs to know how many times to move it. It has that scale factor in it. It needs to know, for instance, if we're going to move this motor at 1 rev per second, let's say it's a micro stepper, it has 25,000 steps to go 1 revolution. That's 25,000. If you think about it, that's a lot. That's almost, what is 1 second? Let's see, if we went degrees, minutes, seconds, I think, and let's see, 360 times 60 times 60 is 25,600, I think, if I'm right. Wesley, check that out. You got your calculator handy, right? We check that? 360 times 60 times 60, I think is 25,600. So we're roughly 1 arc second per step. That means that in order for this microcontroller over here that knows how far to go, is that right, by the way?
No.
1,296,000 seconds.
Okay, so it's 1 minute. What's 360 times 60?
21,600.
21,000. Okay, 21,000. Okay, I knew it was somewhere up there. 21,600 is 1 minute of, and if you wanted seconds, then yeah, so we're basically 1 minute, 1 arc minute of rotation. Now, if you know over here as a programmer, and you know the motion profile, if you know you want this thing to go 1 rev per second at 25,000 steps per second, what's the frequency on this step signal? We want it to go 1 rev per second, the motor to go 1 rev per second. It takes 25,000 pulses to go 1 revolution. What's the frequency that needs to be on this step signal?
25 kilohertz.
25 kilohertz. Right. So that's 1 rev per second and microstepping. That also means that here's part of the problem of using these is you start to look at the outputs that you have, the digital outputs. And if you wanted to go 5 revs per second, all of a sudden, what's that frequency? Math, please.
125 kilohertz.
You got it, 125 kilohertz. What's the maximum frequency out of an Arduino? Anybody know?
It's like, I have to look again.
Yeah.
As the frequency increases, your controller is going to increase in price. So.
Yeah, so this is one of the key things, like, oh, but who said we got to do microstepping? That's advanced stuff, right? So let's not do microstepping just yet. Let's go to page 2 for a minute. Okay. Page 2. Let's go back to this motor. So here we have our motor. We got 2 windings. phase B, phase A. In reality, if we do full stepping, as opposed to way down here, full stepping is that's our low resolution. That's 200 steps per revolution. There's something called half stepping. Guess what half stepping is?
400.
400, right? 400 steps per rev. Now, do you see the difference in microstepping? Was, I said, just a common one is 25,000 steps. So, wow, and this one here required high frequencies. But if you only go 200 or 400 steps per rev, the motor still works. So let's start out with the cheapest system there is, which is full stepping. And that's kind of where we're at with the H-bridge. H-bridge is great at full stepping. Microstepping, just forget it. You're not going to do it with an H-bridge. No chance. It's way too hard. I'll explain when I get to explaining how microstepping works. I'll tell you why. But for now, let's focus on doing this application with something that isn't 120, needs 25 to 125 kilohertz. Let's deal with frequencies that are easy to get out of a microcontroller. So the way you do that is you have a phase A and a phase B, and we're going to go through 4 distinct steps. We're going to make a little truth table here. And first you're going to have the first step, you're going to have A be positive, which means A positive means current runs that way through A. The second step, okay, so, and what happened when you energized phase A and you made it go that way through that coil, the motor went and it moved over there and it lined up with the magnetics that's here, the teeth in the motor. Then, next thing you're gonna do, let me change, you're gonna go, you know what? Hold on. I'm gonna actually color code these things for you. Oh boy, I'm getting fancy now. Plus, all right. So the next one we're gonna go that way through B. Okay. Then, so these are our 2 phases, A and B. Then the next step, we're gonna go that way. We want current to go that way through that winding. And if you remember on the H-bridge, let me just draw a quick H-bridge here. I'll just draw it with some switches. I'm going to draw some, I'm going to be a little bit better. These are connection points. So instead of transistors, I'm just drawing these with switches because it's a little faster. Okay, so this would be A. And so that's one phase. And if you're going to drive a motor, then you're going to need that, times 2 to do the phase B, because you need something to drive phase B in a separate system. So the whole advantage of the H-bridge is that if you want to do phase A and make it go this direction, that's that direction, right? So that direction, and we also want it to go that direction. You're going to have to manipulate the switches so that when it goes this direction, that one and that one is on, and the current, it comes down like that. when you open that one back up and close that and that, now current goes this way and you're good. See what I mean? So you need 2 phases, and then the 4th phase over here, I have a blue left. I have 4 colors total, minus and minus. Okay, so that's what you got to do with the combination of the H bridge and those wires that come out of the motor. You've got to find the 2 ends. Now, why is there, that's 4 wires. What is there doing with 6 and 8 wires? What are those doing? What they did is I'll do this on the A winding here. Let me get rid of this. Okay, what they did is they said, you know what? Let's tap into right here and we'll bring out, let's bring out that, and we'll bring out that. And you essentially take that one winding and give it a center tap. And you tap into the 2 ends of it. It's still about the same winding, but now you have 8 wires instead of 4. Well, that gives you the ability, if you do this, it's the same, isn't it? Okay, so that, when I do that, that's called series. I hooked up on phase A or B, I hooked up the 2 half windings in series and I got a full winding. The other option is to hook up in parallel, and that's basically taking these two windings, and if you have, just draw it over here so it's not the same. And you have this winding over here, you would say, let's run this one to that and this one to that. And then we'll bring out that and we'll bring out that. Or sure, either one. You could do either one. The way I did it made the motor spin backwards. If I'd have brought it out, instead of bringing out this one, if I'd have brought it out here, all that would have happened is the motor spun the other way. There's still windings. It works. But so this one would be wiring the motor in parallel. So these are choices you have, but as soon as you have 8 leads, 1, 2, if they do this for you, you're tied to how they decided to do it. Instead of having the ability outside the hookup on your end to decide how to do it. The good about having 8 wires is that you get to choose how to do it. The bad about having 8 wires is that you have 8 wires to hook up and more to go wrong. And if you're doing a production piece of equipment, that means that every time you build a piece of equipment, you have 8 wires to hook up instead of 4 wires to hook up. So I always have 8 wires in lab because it gives us flexibility to learn, but more and more in the real world, 4 wires is better. And you pre-buy the motor how you want it done from the manufacturer. You don't have it in series or parallel. Okay, so this is what you got to do to drive that H bridge. What you're going to need to do is these transistors are what you're going to control on and off with. And so I need you to, when you go look at the H bridge, I want you to go in to look at the actual schematic for it, the wiring diagram, and you're going to see some additional logic gates. And you're going to start to see, oh, okay, I'm going to need to have something from microcontroller turn off that, turn on and off that transistor, turn on and off that transistor, turn on and off these 8. You have 8 transistors that you need to turn on and off. However, they know that when you're doing an H bridge, that this one and this one always do the same thing together. And so they're giving you the ability to use only 4 outputs, you know, and so one output out of your microcontroller will control 4 transistors, or excuse me, one output controls 2 transistors. instead of having an output for every single transistor and then back in the program telling them to both go on at the same time. You're wiring them and only using one output. You'll see when you go to wire it up, this will become clear. So get into that a little bit. How do you think you're going to wire up to the H bridge? One of the things that I want to look at is what's the difference between, I want to go back to series versus parallel for a minute. Okay, so if I hook these in series, what is this again? What is this thing here? What circuit element is that?
An inductor.
It's an inductor, correct. It's making an electromagnetic field. That's good, the good part of it, but it's also a heater, and that's the bad part of it, right? So, but if we focus on the inductance of this, if you run these two in series, what does the inductance do in series?
Additive.
Right, just like it's like resistors, right? So series is instead of L, oops, it just keeps, instead of L, it now is 2L. Okay, that means the magnetic field got twice as strong. It also means the rise time got twice as slow. So the higher the inductance, the harder it is. Now here, the other thing that keep in mind, we weren't just doing this. We weren't just saying current flow that way and then stop and go to 0. We were saying current flow this way, and then I want you to reverse and flow that way. So we're actually reversing the voltage on the inductor, not just taking it from 0 to positive voltage and back to 0. We're going from plus V to minus V. They hate that. That's a long way to get from positive current to negative current because of di dt. So you need to know that when you have high inductance, when you go to series, you're going to have a lot of torque, but it's going to drop off very quickly because the torque, the faster and faster you go from phase to phase to phase, at some point it never develops full. Remember that the curve for the stepper motor for current and inductor, you apply the voltage and it has a rise time. At some point, if you're out here in the steady state area, you're great, you got full torque. But as you make that motor go faster and faster, at some point you hit this range and this range before it's time to flip it to the next state in the phase table, that A, B, 1, 2, 3, 4. We got 1 is going this way, but by the time it's time to flip it around, it's only actually gone up to here, and it's time to flip around. That means you never developed full current, and that's why the torque on the torque speed curve, I'm sorry, current, time, torque, speed. That's why on the stepper motor, the torque is good for a while, but as you get faster and faster speed, meaning you're taking the current on and off that winding before it reaches full, you start to see the drop off. And that's the good about steppers. They've got natural positioning, so all you got to do is give it a pulse and it moves. You give it a pulse rate at a certain frequency and it rotates. But it's up to you to do that H-bridge stuff and get it to rotate. Okay, so that's something to pay attention to. Now, let's move on to the amplifier part of things. All right, PWM. I drew this out the other day, so I'm not really going to draw it too much again. But this is the key to running this motor is we can't use V equals IR because, as we pointed out last time, by the time you get to the current value, you've only got to like, the resistance is just so low, 1 ohm, 1.5 ohms, that to truly get enough voltage to drive the inductor faster. Remember this V equals L d I dt. So one of the ways that you get this di dt, the current to change faster in that inductor and give you full torque sooner, is to raise the voltage. But if you raise the voltage, well, you also have V equals I squared R. Right? As soon as you raise the voltage, boom, you screwed yourself over here with I squared because resistance is so low. So we have to do something different. We have to break free. We basically have to get rid of V equals IR in the circuit. And the way you get rid of V equals IR is you pulse it periodically. So what happens is when you do that pulse width modulation of the winding, you are able to use a high voltage and get a high change in current, but you're able to keep the average amount of current low. So you're able to control current. So pulse width modulation, current is controlled, I'll just write it out, controlled by the pulse width or the duty cycle of it is another way to say it. Right? And voltage is, I don't know, is it fixed? It's fixed, and you apply it by your power supply. Meaning you're going to pick a power supply and that's your voltage. If you want a different voltage, buy another power supply, right? So you kind of need to think about that at first. What voltage should we start out with? Well, the speed torque curves are going to tell you, when they tell you a certain amount of torque, they're going to give you the conditions that they measured that speed torque curve at, and the conditions are assume pulse width modulation, because that's the only way we even do this. There's a few applications I've done where we use like the old stereo amplifiers that pump, like your audio amplifier is not pulse width modulated, because this signal, this pulse width this is noisy electrically. And it's bad, because think about it, you're turning on and off, amps. You're turning it on and off. This is high voltage. I don't know. Let's pick a number. Let's say you use 36 volts. And you're turning 36 volts on and off, and this frequency, you want to pick something. Generally, the most common frequency is 20 kilohertz. It seems as though you have to go fast enough with your frequency so that it doesn't become V equals IR. If you put in a frequency of, let's say you put in 0.5 kilohertz as your frequency on your pulse width modulator, it's a fixed frequency. Remember, it's not a variable frequency, it's a variable duty cycle. Fixed frequency, fixed voltage, variable duty cycle. So, and then the inductor is the averager in the system. That is your energy stored. Because it's an energy storage device, it stores this as energy in an electromagnetic field, blah, blah. Okay, but if you slow down the frequency to too low, the time here, this time that this is actually on, the on time actually has enough, it reaches steady state and stays on. And when it's on, it's V equals IR. And if it's on too long, you'll burn up your motor. So for instance, little motors, little teeny motors, or I should say little motors, and more specifically, low inductance motors you probably need more like 40 kilohertz to avoid V equals IR in this section right here and leaving it on too long.
Why does
So
that?
huh?
I said, why does that burn the motor?
You feed it too much current, right?
I squared R. Yeah, it's the average amount of current is too much, and the thermal properties of the motor give it hot spots, and you may be right at the average, but the what's the name? That's the thermal. It's a time frame, but basically it's the the thermal time constant of the motor. And if you look up, it's again, you're gonna see when you get to the manufacturer's page, there's a little thing called thermal time constant. And it's a measure of if you apply current, how long does it take the heat to get through and let the motor reach a steady state? And a teeny tiny motor, it starts to get down into less than a minute, 30 seconds, meaning that if it's on for a short period of time, you're going to have tiny hot spots that are so hot that they'll burn up, and it can't get rid of the heat fast enough. So you end up probably not immediately burning it up, but pretty quickly burning up the motor because of these tiny hot spots that are in it that are too hot, and it can't get rid of the heat. So you bump up the frequency, and now it's on, off, on, off, on, off, on, off. It's kind of like putting your arm under hot water. Okay, I'm making this up on the fly. I've never used this analogy, but it's kind of like when the shower's too hot, right? You turn on the hot water, and what can you do? Hot water's flowing down. You could put your arm in it. You could do this all day long, right? Your arm doesn't get too hot. As soon as you put your arm in it for too long, you burn your hand. It's exactly what's going on with the motor. You're doing this the whole time, and you're continually getting it clean. You're getting it wet, but yet you're not leaving it in there too long where it burns it up and makes your skin too hot right there, even though the rest of your body is a nice temperature. See what I mean? Does that help? Is it an analogy?
Yeah, it helps.
Okay, so that's
like running your finger through fire, like a candle flame.
Yeah, there you go. Same thing. Yeah, you can run your finger through, but do you leave it in there? No, right? And so what frequency can you run it through? And the lower the frequency, the more time it has to reach steady state and burn your finger. And that's exactly what's going on in the motor. So you got to run it pretty high. You don't run it any lower than audio frequency. Hobby servos, if you've ever been around hobby servos, they cheap out and they use transistors that can't really do that. This 20 kilohertz is not for normal transistors. I'm sorry, power transistors. These aren't the little guys anymore. These are power transistors. And it costs money to have one that can run at 20 kilohertz. The hobby industry uses 7 kilohertz, and they're in the audible range, but they're kind of counting on that the vehicle is like way over there and you don't care that much, right? You're running it, there's other sounds going on, you really don't care. But if you've ever been around one that's just sitting there, after a while, it's like that noise, the 7 kilohertz noise it's that noise that you can't figure out where it's coming from. I hear it. Is it come from that direction? Where is it? It's somewhere, but you can't find it. And so you're going to use 20 kilo. You'll go ahead and give it a try with your Arduinos. Give it a try, pulse width modulating at 3 kilohertz. Don't do it with a little motor. Do it with a big motor only, because you'll probably burn up the motor at that low. You're too close to leaving your hand in the shower the longest. All right. Doing good. All right. Yeah. Next, wiring. Full step mode. I'm looking at my notes here for a sec just to make sure that I'm on the right page.
I just want to clarify that you meant power equals I squared R up there on the right.
Yeah, sorry about that. Yeah, how about this? Of course I meant that, yeah. Thank you.